Bus. Okay. So we're going to start a new chapter in the book, chapter 15, which is on thermodynamics. This is kind of the longest chapter on this subject, where we talk about like heat and energy and temperature, and thermal, heat, dynamics, movement. So that's like the flow of heat. Kind of a long chapter, and historically, this came about kind of, mostly it was worked out in the 1800s. And it kind of was devised separately. Like it ties into a lot of things like that we're very familiar with now, like conservation of energy. And but this was definitely developed before we knew about atoms. And so some of these ideas in thermodynamics are really things we're already familiar with, but they we kind of approach the subject a little different for historical reasons. Like we're going to talk about 4 laws of thermodynamics. And first law of thermodynamics is simply conservation of energy. But again, they didn't know that at the time. So it was developed in one way, and kind of now we can look at it from a different perspective. But we're going to approach it as in terms of these laws of thermodynamics. Okay, and this lecture is on the zeroth and first law. You might say, why a zeroth law? Well, they came up with, there's 4 overall. They came up with, the first law of thermodynamics, then the second, and then the third. And then someone realized they were missing something that really logically belonged in front, and so they called that the zeroth law, just to maintain the right order. So it's more logical. I'm going to read the zeroth law of thermodynamics. So it says, 2 systems individually in thermal equilibrium with a third system are in thermal equilibrium with each other. So let's see, we have 2 objects that are in thermal equilibrium with a third system. So say we have A, B, and C. Alright, let's say A and B are in thermal equilibrium. So maybe we can just bring them together so they're touching and energy can flow through conduction, but there's no energy flowing here. So they're in thermal equilibrium. Now let's say we bring B and C together, same thing. No heat flow between them. So they're in thermal equilibrium. And then we know that if we bring A and C together, they will be in thermal equilibrium with each other, because they're both in equilibrium with B. And again, that might seem obvious, but it's kind of logically necessary, because when you bring these 2 objects together, heat can flow between them, and we know that it depends on the temperature difference, if there's a temperature difference between them. But logically, maybe it's possible there's other things involved that are required for 2 objects to be in thermal equilibrium. But this is saying, no, it just depends on the temperature. So if these 2 are in equilibrium with this object, they have to be in equilibrium with each other. Okay, so that's kind of just a logical necessity to have this law. And again, it's kind of the last one they came up with, but belongs in front. So we call that the zeroth law of thermodynamics. Should point out, this is what makes thermometers possible. Like maybe B is a thermometer. So you put B, put B in contact with A, it's going to read a certain temperature. Put B in contact with C. If these 2 are the same, if these 2 are in equilibrium with each other, then B is going to have to read the same temperature for both. So if it wasn't for the zeroth law of thermodynamics, then maybe thermometers wouldn't be possible. This whole idea of temperature would not really make sense. So it's very, very important law, even though it's easily overlooked, which they did initially. Okay, now let's get to the first law of thermodynamics. So this involves work, heat, and energy. Now, we know now, like, what heat is. We know it's a form of energy that just flows from one object to another. We just give that the name heat. However, back when they were developing thermodynamics, they did not know what heat was, and for actually a good reason, they thought heat was a fluid. They thought it was like an actual substance. And one thing supporting that idea, well, I mean, you bring two objects together, heat flows from one another, they thought there was a transfer of fluid there. And, one thing that definitely seems to support that idea is that when things heat, they expand. So it's like you're adding fluid to it, it's getting bigger. So it was a very good idea, but it turns out to be completely wrong. And it was a guy named James Jeans, I think, who showed that heat is a form of energy. And like what he did is he had this container of water, and he had this paddle inside, where, picture trying to spin this paddle in the water. That's going to take some effort, but you have to push the water out of the way. And so you're doing work on the water by spinning this paddle. And he was able to show that, like, the energy that it gained, so like if you have some falling mass, you have potential energy. As it falls, it's losing potential energy, which is being converted into work, which will raise the temperature of the water. And he showed that the amount of energy it gained from the work being done on it is equal to the gravitational potential energy that this falling mass lost. And so as Jeans, it showed that that heat is a form of energy. And so that was a very big advance. And now we know thermal expansion, molecules, when they oscillate more violently, they push each other apart farther. So, the idea of heat as a fluid, it definitely made sense at the time. Turns out it's not true. I'm going to change this to internal energy because just to be a little more precise. And I'm going to write the first law of thermodynamics as an equation. And then we'll talk about it. It's kind of a straightforward equation, but we have to be a little bit careful about it. So just writing down the equation, delta U equals Q minus W. So U is internal energy, so we're talking about a change in internal energy. Q is heat, W is work. And again, you can change the internal energy of a gas by doing work on it. Like that paddle wheel, you do work on the wheel, that energy is going into the liquid and heating it up. So you can increase the internal energy of an object by doing work on it. That would apply with gas as well, any fluid. An example of a gas, so you have a cylinder with a movable piston, and there's a gas in here. Now let's say you push down on this piston, the piston is going to resist that. The gas is exerting a force. There's pressure, which is exerting an upward force on the piston. So if you want to push the piston down, you have to do work on it. So you're expending energy. And again, this first law of thermodynamics is just conservation of energy. That's all it really is. So like the energy that you're expending is going into the gas. So that's one way to change the internal energy of a gas, by doing work on it. I was pointing to Q, but really I should have said W. So if you do work on a gas, you're giving it energy, and you can increase its internal energy that way. Now here we have a minus sign. I'm going to get to that in a minute. Another way you could change the internal energy of a gas, say we just put this on under a fire. So we've got a flame here heating up this plate. And so there would be heat flowing into the gas. So what's that doing? That's being absorbed by the molecules. They're moving around more energetically, more internal energy. And so basically, yeah, like I said, this is just the first law of thermodynamics. That energy can change form. It's related to work. If you do work on an object, you're giving it energy. And but it's a little bit tricky though, because Q and W represent heat and work, and those can go in either direction. Like here, actually put this on a hot plate, and then heat is going to flow into the gas. But what if the gas is hotter than its surroundings? Then heat can flow out of the gas. And similarly, I did this example where we're pushing down on this piston. We're doing work on the gas. Well, what if the piston is expanding? And then the gas is pushing this piston, and it's the gas that's doing work on its environment. And so this Q and W, these represent heat and work, but we need to know like what direction things are flowing. Now, there's a convention, which I'll tell you about. Let's look at, well, we already talked about Q. So for heat, Q is positive if heat flows into the gas. Or I should just say, let's keep it more general. Let's just say substance, whatever it is. So if you add heat to something, Q is positive, and then of course Q is negative if heat is removed from the substance. All right. So, again, we had this convention before, and again, it makes sense. You know, Q is equal to Cm delta T. So if Q is positive, delta T is going to be positive. It means you add heat to something, the temperature increases. Delta T would be the change in temperature. If Q is positive, so is that. So if you add heat to something, it adds up. And again, I'm pointing out that, this makes sense, but it doesn't have to be that way. Some books have Q plus W. And again, they just have a different convention. There's nothing wrong with that. But I'm just going with what our book is going with. But yeah, I mean, there's no universally accepted convention here. So this is just what ours is. Our book goes by. So I'm going by that as well. Okay, now work is positive if the gas is expanding. Let's say that. So again, say we have this cylinder with a movable piston and say the gas is expanding, then W is positive. So again, I wrote this down. Now, and then finally, W less than 0 if the gas is being compressed. So again, this is a convention, and you absolutely need to know this. Otherwise, how can you get these things right? However, I did not know this when I started writing it down. It's not, I said you need to know it, but you do not need to memorize this, and I recommend don't even trying to waste your energy trying to remember this convention. So I really didn't know W if it's positive or negative if the gas is expanding. So how did I write it down? Well, it's simple. Let's say the gas is expanding. Okay, so the gas is pushing on its environment. And it's doing work on the environment, so the gas is going to be losing energy. So its internal energy will decrease. And so again, just because of this minus sign, I knew that if W is positive, delta U is negative. And so if W is positive, that means that the gas is losing internal energy, which means it's doing work. Similarly, W less than 0, that means delta U would be increasing because of the work that's going on here. And so that means that you're compressing the gas and you're doing work on the gas. So it's better to understand this convention than try to memorize it or look it up. Just think, like, I don't really ever refer to this. It's good to know the equation itself because, again, it could go a different way, but it's good to just have it in our mind. We're going to accept this equation throughout the whole class and just understand it. Like if you add heat to a gas, its energy increases. If you remove heat, its energy decreases. If you do work on the gas, its energy will increase. So, yeah, if you're doing work on the gas, that means you're compressing it, and then W is less than 0. So delta U would be minus a negative value, which would make it positive. So, again, let's look at an example. It's kind of a simple example. Where, again, we don't want to look at... I erase that convention. Let's not bother with that anymore. So let's say this gas is being compressed. So let's say you compress a gas, and the work is, I'm going to say 500 joules. I'll say the absolute value of the work. We don't know if it's positive or negative. Similarly, let's say while that's happening, let's say heat is leaving the gas. And let's say 700 joules of heat leaves the gas. So again, I'm going to write the absolute value of Q is 700. I don't know or even care if the W and Q themselves are positive or negative. I want to know the change in internal energy of this gas. So actually what I'm going to do is I'm going to erase this equation entirely. So I want to know the change in internal energy of the gas. Well, we're compressing the gas. We're pushing down and doing work on it. And so it would gain 500 joules from that. We're doing 500 joules of work on the gas, so it's going to gain 500 joules. Now, heat is escaping, so it's going to lose 700 joules that way. And the change in internal energy is then minus 200 joules. So again, I recommend, if you have a problem like this, I recommend don't even look at the equation. Definitely don't look at the convention. Just know that if a gas is expanding, it's doing work on its environment. And so that's going to cause it to lose energy. If you're compressing a gas, you're giving it energy. And the heat one's obvious. Heat's flowing in, that's causing the energy to increase. If heat's flowing out, that's causing the energy to decrease. So, for problems like this, it's best not to have that equation. However, we will use this equation later. We'll have to actually use that as an equation at one point. But for now, just the basic idea of the first law of thermodynamics, it's better to just use kind of like common sense than try to memorize conventions and equations. And I think that'll be it for this one. Our next topic is going to be a little more involved. But, first law of thermodynamics. Basically, we're just stating conservation of energy. It just has a different name because this came about before the idea of conservation of energy existed. So that'll be it for this one.